of today's video is going to be atoms and isotopes. So starting at the very beginning here, in the most basic sense, an atom, we know, is the smallest particle of an element that has the chemical properties of that particular element. So we know, based upon Dalton's experiments, that, for example, an atom of carbon is going to be different from an atom of oxygen because those two things have different properties and reactivities. Now, when we talk about an atom, we also know that we can deal with the actual structure of the atom. And this goes back to the experiments of, for example, Ernest Rutherford, who did the gold foil experiment that you read about. So, based upon Rutherford's experiments, what we found is that the atom is comprised of a nucleus, which is the center, the very dense part of the atom, which is comprised in turn of protons and neutrons. Alright, so we know that the protons are the positively charged particles inside of the atom, and the neutrons are also fairly heavy particles like protons, but they carry no charge. Those again are in the nucleus of the atom, which comprise the very center of the atom. Outside of the nucleus, we have the so-called electron cloud, which is primarily going to be empty space inhabited by electrons. Now, the electrons are very, very tiny particles when compared to protons and neutrons, and they carry a negative unit charge. All right, so we'll talk more about atomic structure later on in the course, but for now we want to focus in again on some of these subatomic particles that we just mentioned. So as I mentioned, the electron is going to be the negatively charged particle in the atom. It's found in the electron cloud, which is primarily volume but very, very low density, so primarily empty space with these tiny little particles floating about in it. So in terms of relative charge, not ideal charge or actual charge, but relative charge, the electron will carry a 1- charge. It's the negative particle in the atom. A proton, as I mentioned before, is going to be a heavier particle. It's found in the nucleus. It carries a 1+ unit charge. Neutron, then, also found in the nucleus, will be of comparable mass to the proton, but it carries no charge. It's neutrally charged. In terms of mass, as I mentioned, the electron is by far the smallest and least massive subatomic particle we find in the atom. And in terms of its relative mass, the AMUs, which stand for atomic mass units, which we'll define in just a moment, we see that the electron has a mass of 0.00055 AMUs. In contrast, the proton and the neutron are almost equal in mass, and you can see their relative masses in AMUs here. So essentially, almost equal in mass and about a mass of 1 AMU, respectively, for your proton and your neutron. So, as I mentioned, the AMU is going to be a relative mass unit that we're going to use to describe really, really tiny particles, things like subatomic particles, things like atoms, and even individual molecules. We use it because it's a convenient mass unit to use as opposed to grams, because we're talking about such tiny things. As I mentioned, the AMU is a relative mass unit, and by definition, it's going to be 1/12 the mass of a single atom of carbon-12. Carbon-12 is a very specific isotope of carbon atom. We'll talk a little bit later about what isotopes actually correspond to. Also, we can have a conversion factor between AMUs and grams. And what we will find is that 1 AMU is actually equal to 1.6605 times 10 to the minus 24th grams. So as you can see here, in terms of conversion to grams, an AMU is an extremely tiny particle. Alright, so picking up, what we find here is that atoms are going to be described by the number of protons, neutrons, or electrons that they have. So, for example, if I take a look at the total proton count in an atom's nucleus, that will tell me, for example, what the identity of that particular atom is. If I add the protons and the neutrons together, for example, that will give me an approximate mass in AMUs of that particular atom. So let's take a look at how we characterize these things. So for any atom, we can define first an atomic number. Now the atomic number, by definition, is the number of protons in the atom. And as I mentioned, that's going to define the identity of that particular atom. So for example, anytime I have a carbon atom, that carbon atom is defined as a carbon atom because it contains 6 protons in its nucleus. In contrast, an oxygen atom is defined as an oxygen atom because it contains 8 protons in its nucleus. And likewise, a hydrogen atom is defined chemically as a hydrogen atom because it contains only 1 proton in its nucleus. Now, the other thing that we can look at is the number of electrons present in a particular atom. Now, what the number of electrons tells us about the atom is the actual charge on the atom. So, for example, a carbon atom is a carbon atom because it contains 6 protons. That will never change. However, the number of electrons in the electron cloud around that nucleus can vary depending upon the chemical conditions surrounding that particular atom. So, for example, if I have an oxygen atom that has 8 protons in its nucleus and also 8 electrons in its electron cloud, we'll see that the 1 plus charge cancels with the 1 minus charge because I have 8 of each. And as a result, that particular atom will carry no charge, and we say that the atom is a neutral atom. However, oxygen atoms can exist in the oxide state, which carries a 2 minus charge. What that means to us is that we still have 8 protons in the nucleus, but now we have an extra 2 electrons in the electron cloud, and the atom does that to gain stability. Alright, so if I have an extra 2 electrons in the electron cloud for a total of 10 electrons, that means that I am going to carry a net 2 negative charge or 2 minus charge on that oxygen atom. So as a result, what we form is an ion. And an ion is nothing more than a charged atom. Now, an ion can be negatively charged, as in the case of the oxide ion that I've shown you here. Any negatively charged ion will be called an anion. Likewise, I can have a situation where we will have a deficiency of electrons, and the atom in that case will take on an overall positive charge. In that particular case, I would have what's called a cation. Alright, then finally we have to think about the mass number. The mass number is going to define the approximate mass in AMUs of a particular atom. So in the mass number, what we care about are the protons and the neutrons. So the mass number will be given as the number of protons in the nucleus plus the number of neutrons in the nucleus for a particular atom. And again, that gives us the approximate mass of the atom in AMUs, because as you'll recall, an AMU is going to be the approximate mass of a proton or a neutron. Now, what we can do is we can now represent a particular atom according to its atomic number, its mass number, and its charge. So we use the following symbolism for that. So what we do is we use the symbol from the periodic table for that particular element. So carbon, of course, has the symbol of C. So I write that symbol down. And in this particular case, I can put the atomic number down here on the lower left. So I know that a carbon, to be a carbon atom, has to have 6 protons associated with it. So that's what that 6 here represents. So carbon will always have a 6 on its lower left. As a matter of fact, that's understood, so in many cases that number is often left out. However, we also need to represent the mass number here. So in this particular case, this is what we call a carbon-12 atom. And the reason we call it that is because it has a mass of approximately 12 AMUs. Where does that come from? It comes from the fact that this particular isotope of carbon, which is a particular type of carbon atom, has 6 protons in its nucleus as well as 6 neutrons to give me the total number of 12. If the atom were to carry a charge, I would put the charge on the upper right, as I did here in the case of the oxide atom. So in that particular case, I don't have a charge here, so 0 is understood to be a neutral atom and I leave it off. But if this, for example, were an anion of carbon that contained an extra, say, 2 electrons, I would put a 2 minus charge up here on the top right. The very last thing I want to touch on in this video, folks, is going to be the concept of isotopes, because I did bring it up in the previous part of the video. So an isotope, as you probably know, is an atom of a given element that can have different masses. And how do we get different masses in a particular element? Because we know that the number of protons has to remain constant for that element to be that element. And also, the electrons are so tiny, we really don't include them in the overall mass. So the only other option that we've got is for the number of neutrons in the atom to vary. Alright, so for example, we have 3 known isotopes of carbon. We have carbon-12, we have carbon-13, and we have carbon-14. We've already seen carbon-12 because we know that that is the basis of the definition of the AMU, or atomic mass unit. We know that an AMU is 1/12 the mass of a carbon-12 atom. So when we actually take this apart and look at it, what we see here is that the carbon-12 atom will have 6 protons associated with it. So if we wanted to calculate the number of neutrons in here, we can do it by the difference between the mass number and the atomic number. So 12 minus 6 gives me 6. So I know that an atom of carbon-12 has to contain 6 neutrons. Now, the other thing about these isotopes is we have to think about their relative abundances. What we find is the vast majority of carbons out there in the world actually exist as carbon-12 isotopes. As a matter of fact, 98.89% of all carbons are carbon-12s. Okay, so about 1 in every 99 carbons that exist as carbon-12 isotope. Another isotope of carbon, which is a lot rarer, is called the carbon-13 isotope. Now again, it's carbon-13 because it has 1 AMU greater mass than carbon-12. Now again, it has to have 6 protons in its nucleus. Have 6 protons in its nucleus. If we want to calculate the number of neutrons in here, again, we just take the difference between the mass number and the atomic number, and what we find is an atom of carbon-13 will have 7 neutrons in it. Again, a much less abundant form of carbon. Only about 1 in 100 carbons exist as carbon-13. And then the final isotope, which is kind of interesting, is a radioactive isotope of carbon. It's very, very rare. It's only found in the smallest trace quantities, so we really don't give it a number here in the total percentage. But it does exist. And I'm going to let you calculate how many neutrons there would be in an atom of carbon-14. So what we're going to do in class next time is we're going to talk about how we can actually calculate average atomic masses based upon masses of individual isotopes and their relative abundances.